Welcome to a lesson with Dr. Powell. Let's take a look at an example of a function that preserves an operation and transfers it to another one, and what it does with things called um, identity and inverses with respect to an operation. First of all, this function is log. You could say log base 10 if you want. Now, what it does is it takes a set. Let's just take the set of positive real numbers. So it'd be like the domain. So it takes that set in here, and what does it do to it? Well, let's think. We're gonna get some structure on it. Let's suppose that we think of a multiplication type structure. So we have kind of multiplication. Oh, we'd want positive real numbers, not equal. So positive real numbers, a multiplication structure on the positive real numbers, such as, so if we have a sentence like A times B is equal to C, then we should expect that the log function is going to transfer the structure. But it doesn't transfer multiplication to another multiplication. We take it to the image of multiplication, log times log A log B should be equal to log C if structure is preserved. Let's see if this is accurate. Well, log times, so the image of this operation is actually addition. So we have log A plus log B is equal to log C if we had A times B equaling C up here. It's the same thing as we could just replace C with A times B, and this is nothing more than a log property. This log property actually gives us the transfer of this operation. Now, in multiplication land, we have something called an identity. An identity is an element such that when you multiply it to another one, it retains its identity. So A retains its identity after multiplication by 1. So 1 is considered an identity with respect to multiplication. So a multiplicative identity. Now, what does log do to that identity? Well, log of 1 is equal to 0. Think about that. 0 is actually an additive identity. Well, that should make sense because addition is the image of multiplication via the log function. That's what it was transferred to. And the logarithm, it transferred a multiplicative identity and sent it to an additive identity. So if a function preserves structure, it will also preserve identities. So send multiplicative identities to additive identities. It also does, so we've talked about what a structure preserving function on an operation like multiplication or addition does with identities. Now, what does it do with inverses? Let's think about that for a minute. Okay, so, well, we need to know what a multiplicative inverse is, first of all. And that's something that undoes identity completely, or undoes, instead of preserving it, it undoes it. So suppose we have A, and if we multiply it by 1, supposing that A is a positive real number, so it's not 0, and you multiply it by 1 over A, think what happens. These cancel and you end up getting 1, which is the multiplicative identity. And so what you've done is these two guys are inverses of each other. Whatever you multiply something by to get back to the identity is an inverse. So for instance, 2 times a half is 1. So 1/2 is the multiplicative inverse of 2. And 2 is the multiplicative inverse of 1/2. Let's see what a log function would do with an inverse pair. In fact, let's even just look at that sentence right there, that multiplication sentence, 2 times 1/2 is equal to 1, and apply a logarithm to it, because we know logs preserve the multiplication structure and change it up. So let's see what it does. Log of 2, log times log 1/2 equal to log 1. Notice this becomes plus, this becomes 0. Notice something. Log 2 plus log 1/2 is the additive identity, which makes these guys additive inverses of each other. In particular, if you think about a log property with exponents, this should be very clear. If we just look at log 2 to the negative 1, negative comes out, and we get log 2 minus log 2 is 0. So yes, adding negative log 2 to log 2 makes 0. So they're additive identities, or additive inverses of each other. Thanks for watching.